Hi, Ben with Novelux Stereophonic. In front of us on the bench here today, I have a pair of amplifier modules from a set of ADS or Braun LV1020 active studio monitors. A customer of mine is an avid ADS collector, and he recently came into a set of these speakers and asked me if I would assist in getting them restored. So he's going to be working on the cabinets and the drivers, and my part of the restoration is going to be getting these amplifier modules back up and running. So he brought them over today, and we did a quick triage test and determined that this chassis is fundamentally working, but this chassis has some issues. So in this video, I'm going to be going over the diagnostic procedure, repair, restoration of these modules. We'll do some testing and analysis, and then in the end, we'll get them loaded back into the cabinets and see how these speakers perform. So if that sounds cool, stay tuned. Okay, so to do this at the bench right now, it's a little bit messy. If I ever start consistently working on this model, I'll end up building some sort of jig or breakout box to make this a little bit easier. But the gist of it is what's going on here is I'm taking the connections for the speaker outputs and feeding them into my dummy loads over here on the patch panel. And then I have the AC mains coming into the blue and the black wires, and there's a little thin wire that comes off of here that is the coax for the input. So I've got all my connections just wired up with clip leads here, and then I have two of the outputs going into my Sencor PA81 at 4 ohms, and then the other driver is just hooked across my static 8 ohm load going into this Siglin oscilloscope. So the mid-range is an 8 ohm output, and the tweeter and woofer are 4 ohms. So I've got the Sencor set to 4 ohms, we're 8 ohms down here, and then I just have to get this connector plugged into the bottom of this amplifier. I found the easiest way for me to do this is to put it up on the side, and I just use a hockey puck here to support the chassis so it's not able to tip over. And then I can plug in this interface block right into the back of the amplifier module here. All right, I think I have everything in frame here. I'm going to turn this on. Okay, so the power amplifier is on. We're going to be looking at the treble and the bass on the left scope, and we're going to be looking at the mid-range on the right scope. So I'm going to turn on my test signal. I'm feeding a small test signal in at 1 kilohertz. I'm just going to up the amplitude a little bit here. So at 1 kilohertz, we have a nice strong signal on the mid-range here. And what I'm going to do is just change the frequency. So I'm going to ramp this up in 1 kilohertz increments. So that's 2 kilohertz, 3, 4, 5. And what's going on here is the red trace is my high frequency. So that's the high frequency amplifier. And as we manipulate the frequency, you can see the higher we go, the bigger the red trace gets, and the smaller the blue trace gets. Likewise, if we go down the other direction, I'm at 1 kilohertz now. If I start ramping this down, we'll see the blue waveform for the mid-range will go down, and the yellow waveform for the bass will go up. So right now I'm at 200 hertz. As I continue to go down, it gets bigger until it flattens out. So you can see how the active crossover is working here in real time as I sweep the frequency. So this is the amplifier module that's fundamentally working. So next up, I'm going to hook up the one that's having issues, and we'll see what those waveforms look like. Okay, I've switched it out. I have the second amplifier module connected. We're going to power it on. Okay, the red light is on, and I'm going to feed it that same 1 kilohertz signal, and all of the level settings are right in the middle. So I've got it on, but I have no output. So nothing's showing up here. Let me raise the frequency. And I'm gonna go to 15 kilohertz. And we can see there's a little bit of something here. I'm just gonna start ramping up the signal. And we can see that something is happening there, but it's not looking very good. If I go to the frequency and I take this back down to 1 kilohertz at that level, you'll see there's a little bit of a signal here, but I'm feeding this way more signal than I needed to get the other one to work. And you can see that my waveform is not clean. So that's what the mid-range looks like. Let's take this down and look at the bass. So I'm going to go to 200 hertz. And we can see that yellow trace down there Let's see if I can zoom this in. We're having a similar issue on the bass, so we're not quite getting the correct audio signal through this amplifier. So I did some initial probing around, looking for the usual suspects, out-of-spec capacitors, shorted transistors, things like that, and I didn't really find anything in the output stage. So then I moved on to this section here, thinking since it's across the board, maybe it's the signals that are coming into this active crossover that are getting messed up. And luckily this is super easy to remove. So there's a pin connector, almost like an old vacuum tube socket here, that this interface pin can come out, and then I just need to remove the screws that are holding this thing in, and this whole module can come out. Okay, so this is what that module looks like. And I know just from experience that this specific type of capacitor has a high failure rate. I see a lot of the Braun body ones in vintage hi-fi equipment, and they're almost always bad. They're replace on-site capacitors for me. I haven't dealt with these gray ones yet, but I have a feeling that some of these are going to be bad, especially since there's evidence that a couple of them have already been replaced at some point in the past. These don't look original. These are Japanese capacitors where everything else in here is European. So I have a suspicion that some of the caps might be bad in this board. But what I'm going to do is grab the known working board out of the second module, swap it into this one, and see if this one will run. So looking at this, you can see in the other one, this capacitor was changed. So somebody's definitely been in here doing stuff before. So like I said, my guess is some of the other ROE branded capacitors are going to have failed in that board. But this is the known working board. Let's sub this in and see what happens. There's 4 points here with these little standoffs. I'm just going to be using 2 of the 4 points just for ease of connection, because I'm going to be pulling these right back out. Okay, board is swapped. Let's flip this thing up and do the test again. Okay, I've got this powered up. I'm going to start at 1 kilohertz with 500 millivolts, peak to peak, same as I did on the first module test. And look at that, we have signal. So let's do some sweeping. So that's 1 kilohertz. You can see the red trace going up as I increase the frequency, blue's coming down. Let's go the other direction. You should see yellow going up. Yeah, so it looks like that's fundamentally working. So the issue is definitely in that active crossover module. So that's what I'll look into next. Okay, so I ended up sorting out this board, but it was a strange issue. So first off, I started by checking all of the capacitors in circuit, and the only ones that were suspect are these green ones that had been replaced in the past. I pulled these and they're both bad again, so I don't know what the deal with those was. All of these tested fine in circuit, so I went around and compared the boards with my trusty octopus tester, and I couldn't find a difference between the 2 boards. So eventually I resorted to just shotgun replacing these caps. Even though these all tested good in and out of circuit with the Peak Atlas tester, it was replacing all those caps that ended up fixing the issue. So now with this board in, it matches the performance of this one, at least fundamentally. So I'm going to do some more detailed testing on these and see if I can figure out why one or more of these was causing that board to act up. This Peak tester is extraordinarily good at finding faulty capacitors. But for some reason it didn't catch this error, so I'm going to go through here and make sure I didn't make any mistakes in measurement. So this is one of those ones that have been previously replaced. This is supposed to be 10 microfarad. It's, you know, almost 40% under, and high ESR, almost 30 ohms. This one's not terrible. Let's check these ones. These ones are also supposed to be 10 microfarad, 63 volt, and they're all measuring high, but very low ESR. These must have been really high quality capacitors. The ESR is very, very low for an electrolytic. Ooh, that one was bad. Maybe that was the culprit there. Check this out. So this one has some sort of brown residue on the side. I think maybe I just missed that one in the testing. Because I remember seeing another one with a brown leg like that, and it tested great. See, that one's fine again. They're a little bit high, but that shouldn't keep it from running. And unfortunately, I just shotgunned these. Well, there's another bad one. You know what? I was testing with a different set of probes and wondering if that was the thing that didn't catch these. I just put on these grabber probes. I completely forgot I had them. These are working really, really well. Oh, here we go. Let's see. Is that where we're gonna go? Yeah, thought that was open for a second. That's fine. Oh yeah, so this is the one that I found, and I think it tests good. Let's see. Yeah, that's good enough. That's actually tests better than most modern brand new caps. So even though this one has this leakage or something going on, it's not working properly. So I guess I did have two bad ones here, and this is probably the root cause of these issues. So that one, see, now it's testing with only 1 microfarad or 1 ohm of VSR. This is the one with the brown leg. Yeah, see, now it's passing. So I don't know what's going on here. I'm going to take these two at least and put them on the Sencor LC102 and see what happens there. Okay, let's set up the LC102. We're gonna do aluminum electrolytics, 10 microfarad at 63 volts. So this is going to test it almost at rated voltage. So I'm gonna start with the two that failed at one point on the peak. Okay, let's see how this does. Showing about 15 microfarad. Let's see how it does for leakage. I'd say that's pretty bad. I'll throw a new capacitor on for comparison. This is what I put in temporarily, one of these Worth caps. So let me find the positive and negative on one of these. This is very close together. I gotta make sure these don't touch. Okay, so I'm set up to test one of these. Let's see how this one does. Almost on the button for 10 microfarad. Now let's watch how fast this leakage goes down. Basically non-existent. It immediately went to good and it's in the microamps. So that issue was almost certainly caused by these capacitors going bad. And I should have trusted my gut from the beginning and just started with these. It would have saved me a lot of time, but I wanted to give them the benefit of the doubt. I like to do my troubleshooting by isolating a single component instead of just shotgunning parts, because I don't learn anything otherwise. So now I'm testing this one that had significant signs of physical leakage, and let's see how this one does. Value slightly high, but not too bad. Let's check the leakage. And again, taking way too long to come down. Okay, so it looks like these were definitely the culprit for that channel not working. So I'm going to replace every single one of these in this unit. These just aren't reliable capacitors for the long term. Okay, before we get much further, I did want to talk a little bit about the topology of this amplifier. So this is a triamp design, meaning there's 3 individual power amplifiers in this chassis, one for each driver. So the base amplifier is here, mid-range, and treble here. The topology of the amplifiers themselves are what are known as quasi-complementary capacitor coupled. So the quasi-complementary refers to the output, the final output transistors being identical polarity. So they're both NPN transistors. You can see the model number is 2N3055 for both of these. And then the capacitor coupled comes from the way that the amplifier delivers the audio signal to the speaker. So in this amplifier, the audio signal is generated here at the midpoint between the two output transistors, and then there's a capacitor here that blocks this DC from getting to the speaker and lets the audio signal pass through. Our B plus is about 58 volts DC, so the ideal level for this middle point is 29 volts. If this varies significantly, what you'll get is asymmetrical clipping. At higher output powers, one half of the waveform will clip before the other. So you always want this to be almost exactly centered between ground and the positive supply. So that's how all of these work, and they're just built a little bit differently, each one of them, to provide the necessary power for the driver. And you'll notice that in the tweeter section, the transistors are these little guys here, where we have actual big TO3 package transistors for the mid-range and the bass. These are the coupling capacitors, and the frequency is specifically chosen for the bandwidth of that specific amplifier. So these ones are each 1,000 microfarad, I believe, is what the schematic said, and then this one is quite a bit larger for the bass. So what Braun has done with this design, I think, is actually a very good way to execute an active speaker. Some people would argue that going with a capacitor-coupled quasi-complementary design, that you're sacrificing some performance and you could get better sound out of a true complementary direct-coupled amplifier. But along with that comes a lot of extra complexity. You have to add a negative power supply and probably some extra protection circuit for the drivers and things. With this, it's a very simple execution, single positive power supply, and it's serviceable. It's easy to work on. Going along with that, by going with an active crossover, you're saving on all the expense and the downsides of having big inductors and capacitors that you would get in a conventional passive speaker. And you also get the flexibility of being able to electronically adjust your bass, mid-range, and treble to your liking. So it's a really good way to execute an active speaker, in my opinion. And another bonus is when you have a designer like Braun that is building an amplifier specifically for the speaker that they're building, I'm sure the engineers took time to make sure that everything was matched up exactly how it should be. If you're designing your own system from scratch, picking out an amplifier, picking out a speaker, sometimes you'll get really lucky and find a really good match, an amplifier that's a perfect match for a specific speaker, and it just really performs well. But if you bought a highly inefficient speaker and then decided to buy a single-ended triode tube amplifier, you might be in a world of hurt. So a design like this takes care of everything because it's all built in one neat package. And I'm excited to see how this thing performs when it's all done. So the next steps here, I'm going to go through and do a full recap on this. We've already seen that a lot of these caps are not reliable long term. And then I'll probably refresh the thermal compound and all the output transistors and just give it a good once over, clean everything, and then adjust the bias. There's some level adjustment that can be done up here. We'll go through all of that and get these things in tip-top shape before they get loaded back into the cabinets. The parts came in for this project, so I went ahead and reworked this first chassis. This is the one that was marked bad. I wanted to tackle this one first. The reason that I didn't do this on camera is because it's my first time working on this specific amp, and I wanted to learn a little bit more about the circuit as I reworked it before I started to talk about it. So I'll be covering this chassis in a little bit more detail as I go through it. One of the challenges with this project is that the only available PDF manual is in German, so I had to do a bunch of Google translation to understand the calibration procedure, which we'll go over in detail, at least how I understand it, when this chassis is done. But this one all tested out pretty well. There might be some ways to optimize this. I might need to change out some resistor values just to get them more accurate so that the channels balance to one another. In my testing between this chassis and this chassis, they have a slightly different input sensitivity. So the same voltage fed into this one creates a slightly lower signal than this one, and that could result in channel imbalance. I haven't measured it with a dB reference to see how far out it is yet, but that's something that I'm going to probably try to resolve once these are both rebuilt and I can compare apples to apples. So that's what's next. I'm going to start rebuilding this chassis, and then we'll go through the calibration procedure once all the new caps and stuff are in. Since this chassis is all currently up and running, I'm going to rebuild it in sections and test as I go. So I'm going to start with the active crossover board. We'll do a full electrolytic recap on this one, new trimmer resistors, and a new Zener diode, and then I will hook it up and we'll do a quick function test before moving on to the power supply and power amplifier. The recapping of this is pretty straightforward. It's just like for like, but these trimmer resistors, what I like to do is pull them and measure the the resistance before I put in the new part so that it kind of sits exactly where it was. Now I took some reference measurements here and they're slightly off of where they should be. So I'm interested to see if I just do the recap on this and retest it, because I know some of these caps are probably on their way out. I want to see if that makes a difference. So after this whole board is rebuilt, we'll throw it back in and check it against my reference numbers and see where it's at. Okay, I just finished the recapping on this board. All of the small radials were 10 microfarad. The schematic says something different. I think it says 1 microfarad. But I went with what was in the boards. Both of my boards were the same, so they all got 10 microfarad caps there, and then just a couple axial electrolytics up here and the Zener diode. Now you can see these trimmers are still original and they're very tarnished. I could just clean these, but it was a pretty common value and shape to get, so I just ordered some replacement parts. Now, before I pull these out, I'm going to try to measure them in circuit and out of circuit and see how that matches up. So one trimmer is here, the other one is, let's see, it's going to be right here. Okay, so I'm just going to check. All right, so this is the wiper, and got about 2K there. So this is supposed to be a 2.5K pot, so I should have about 500 ohms on this side. Okay, and then on this one, where are we? Here. We have 1.8K on one side, and that's 1.2. Let's see if this shows us. Yeah, that's showing around 3K there. So this whole control is supposed to be 2.5K. It's a little bit out of spec. And then this one, let's see if this measures here. Yeah, that's closer to 2.5. Anyways, I'm going to be replacing both of these with 2.5K, so I'll do that next, and then we'll remeasure once I get the controls pulled out. Okay, so I'm going to add some alligator ends to my probes here. We're just going to verify that this is the same out of circuit. So let's see. Go between this leg and the wiper. That's showing about 1.9. Yeah, so this is measuring in and out of circuit the same. So what I'm going to do is grab my new trimmer, and let's see how these do across the entire element. A little under 2.5, but what I'm going to do is just set this side to 1.9. And I think for some reason this control, most trimmers when you take them out of the package, they're going to measure right in the middle of their range, but this manufacturer has set them all the way to one side. So I'm going to set this at about 1.9. And the other side should be about 540 ohms, but it's going to be low because this one's not as big. Oh, sorry. I have to go between the wiper. Yeah, so it's going to be a little bit different than the control that was in there, but this will be close. All right, let's see how the second one does. That one fell right out. I don't know if we're going to be able to see this. It should read 2.5K there. I'm going to grab some alcohol and see what happens if I scrub on this a little bit. On the other board, these were both marked 2.5K. Yeah, 2.5K. So this carbon is just out of spec. It's about 3K ohms across the entire element rather than the 2.5 that it's marked. So again, if I go over the entire element, showing closer to 3K, and I'm just going to copy this value again here at 1 point, it's about the same, 1.9. So we'll throw that back in, and then at this point we can put this back in the chassis and see how it's working with the new parts. Before I load this board back in, I'm going to clean all of the pins on this connector. I'm just going to use a couple things. And this is kind of how I clean vacuum tubes as well, so I'm just going to use a little bit of deoxit D100 and just get a little bit on each one of these, and then use a little piece of foam. And this will act as kind of like a little abrasive. All right, cotton swab. And I could go crazy and get all of the black tarnish off of here, but that's not going to be making contact inside of the socket. Just going to add a little bit more deoxit and then work it in and out of this control, or into this socket, which will help clean it out a little bit. Okay, so now I've got 4 spacers to put in here, 4 standoffs. Where are they? Those are these things, so I will put in all the standoffs and the screws and then set this up for a quick test. Okay, I've got this reworked card loaded back into the chassis, and now I want to go over the procedure for calibrating the levels. So again, this was all in German, so I just did some translation with Google and then condensed everything down. So first off, we have to load the treble and bass amplifiers at 4 ohms and the mid amplifier at 8 ohms. We set all of the front panel controls to 0 dB. And that's important. We're basically setting up the reference point so that when all the controls are at 0, they're giving us the values to set these trimmers to so that everything is flat when it comes out of the speaker. Once we feed in that 100 millivolt signal, we should get a signal of approximately 1.9 volts RMS on the tweeter output, and then we're going to trim the signal generator until we get exactly 1.9 volts RMS. Next up, we're going to keep the amplitude of the generator the same, but we're going to change the frequency from 15 kilohertz to 40 hertz, and then adjust one of the trimmers so that we get 1.6 volts RMS out of the woofer output. Then we're going to change the frequency and look for 0.9 volts on the mid output and trim that out if we need to. Now, when I did these measurements before making any changes, it took me 111.3 volts RMS to drive the tweeter to the 1.9 volts, and that's different than when I tested the amplifier that I've already fully rebuilt. That one took like 97 millivolts RMS or something. So I'm wondering if I will get a change or if this is going to be the same. If that's the case, I'll have to adjust some voltage divider resistors or something to get the amplifiers equal. So I'm going to proceed with this test. The way that I have these meters set up is this is just tied across the tweeter load, woofer load, and mid load. So I'm going to sit down here, and we're going to feed right now the signal. I'm not going to move the camera so we stay in the meters, and I'll just describe what's going on in the signal generator. So I have the frequency set to 15 kilohertz. Let me power on the amp. Okay, so frequency is at 15 kilohertz and amplitude is at 100 millivolts RMS. So this is our tweeter, and see, we're close. So with their recommended 100 millivolt test signal, I'm close but not quite. So I'm going to adjust this very slowly down until we hit 1.9. All right, so I'm at 1.9 volts now, and I'm at 96.9 millivolts. So just changing those capacitors and parts out was enough to correct that discrepancy in input voltage. So this is testing very similar to my other rebuilt amplifiers so far, so that's a good sign. All right, next up, I'm going to keep that level at 56.9 or 56.8 millivolts RMS, and I'm going to alter the frequency to 40 hertz. Now we're reading here on the base one, but this one is supposed to be 1.6 volts RMS. So I'm going to grab a adjustment screwdriver and locate the base control, the trimmer on the board, and I'm just going to rotate that until we get 1.6 volts. That's close enough there. And then we're going to change to 1 kilohertz. And on the other one, I couldn't adjust this out. So this is our mid-range output. So I'm gonna get on the other trimmer. On the other amp, I needed to turn this all the way down, and I got to like 0.93 or something. So we'll see if this one can make it all the way. Yeah, that one can even go under. So I might have to adjust some resistor values in the other amplifier, but this is what we're looking for. So 0.9, 1.6, and 1.9. So I'm going to go through those frequencies again. We're going to go to 15 kilohertz, 1.9, 40 hertz, 1.6, and 1 kilohertz, 0.9. So those trimmers are calibrated, and we can move on to working on the power supply and power amplifier. The next thing that I'm going to tackle is the replacement of these power supply capacitors. The original ones are stud mount, so these are the ones that I pulled out of the other unit. So it goes through the chassis and then mounts with a little insulator. So this gets mounted to the chassis like this, and the connections are done up top. Capacitors like this are getting pretty hard to find, so I'm going to replace them with snap-in caps. So this is what's going to replace the big cap. This is a Kemet cap, and these are just clips that I had in my stash from various projects that I've worked on in the past. And then I actually ordered a 35 millimeter bracket from Mauser to do this capacitor here. So this is the one that's going to replace the smaller one here. So what I'm going to do is desolder the connections. I'm going to add some ring terminals to make them easier to mount up to the new caps, and then I'll drill some holes in the chassis and basically mount these on top of the old stud hole, so they'll be in the same spot as the originals. I have the main filter capacitors replaced here and here, and next I'm going to move on to the amplifier module. This is going to be pretty straightforward. I'm just going to do a replacement of all the electrolytic and tantalum caps, and then the trimmers for bias. I'm going to be replacing the trimmers in a similar way. I'll get a reference measurement on them first, set the new controls to about the same, and then I'll go through the bias adjustment procedure in a little bit. This is a capacitor coupled output stage. These are the output coupling caps. So these are selected and values that are appropriate for the frequency. So on the low frequency, the value is a little bit higher so that it doesn't roll off the lows. And then on the mid and the highs, it's not necessary to have a cap of the same value because the crossover is rolling off those frequencies anyway. So these are a little bit smaller. And what I'm going to do there is replace those axials with an audio grade radial. So this is directly in the signal path, and axial capacitors in these values are very hard to find. So I went with an audio grade radial capacitor, and what I did is I took the positive lead and I'm just going to have it point straight down. So that'll go on one side of the connection, and then I'll bend a 90 here, and that will point straight down, and that'll allow me to put a radial cap in the physical position of an axial without it looking wonky. So that's what I'll be doing there. I'll come back once I have this fully rebuilt, and then we'll power it on and set the bias. The amplifier section is now reworked. You can see my axial capacitor replacements here. I also dusted off the board, cleaned up some of the thermal compound mess on the back, and then replaced the bias trimmer. So just like I did earlier, I took a reference measurement off the bias trimmer before I replaced it and set the new controls to the same value. It's still possible that they're slightly off, so I'm going to do a careful first power on with dim bulb on this, and that's what we'll be going over next. I'm going to be setting the bias, and to set the bias on this amplifier, you pull each one of these fuses, one for each channel, and that interrupts the positive power supply rail. And in the place of the fuse, we put an ammeter, so we can measure the current flowing through the entire amplifier channel and adjust this trimmer to the appropriate value. So I'm going to pull these fuses and connect some meters, and I'll be right back. Okay, back to the manual. So I translated this section, and basically it's asking me to set the bias across the fuse holders with an ammeter. The base amplifier is supposed to be drawing 35 milliamps at idle, mid 30 milliamps, and treble 25 milliamps. So I have each one of these meters set up to measure current, and I'm connected across each one of the fuse holders. This is base, mid, and treble. So I'm going to turn this on, and what I like to do on a first power up like this is I do this on dim bulb, and then I'm just going to verify the directional rotation of each one of the controls and take the bias down from where it is. Then I'll put it on full power and actually set the bias. So right now I'm going to turn this on. And we can see we're pretty darn close to where we need to be. So setting my reference levels worked, but what I'm going to do is go to each one of the controls. I'm going to start with base, and I'm just going to turn this down slightly. Oops, I have the wrong screwdriver, and it looks like the rotation is counterclockwise. So I'm just going to go to each one of my trimmers and turn it down a little bit before I go to full power without dim bulb. And then I also like to just check here that everything is still working, because I did replace a bunch of capacitors. So I'm going to feed a test signal in, and you can't see it on the scope right now, but you'll see my current increase on my mid-range. I'm at 1 kilohertz. Let me go to the 40 hertz, and we should see our current rise on this one. And then if I go to 15 kilohertz, our current goes up here. I'm going to go ahead and power this down. I'm going to switch my connection over to full power, so no dim bulb in circuit. And these values should be almost exactly the same. I wasn't doing much current limiting at all. Power this on again. Okay, and now I'm going to go for my target values. So let's start with the base at 35 milliamps. There we go, mid. And the locations of these controls are pretty self-explanatory. They're just right next to the output transistors for each channel from left to right. Am I looking for 25 here? Right, so I just need to tweak the mid-range a little bit. Now these are going to fluctuate with temperature. The manual says to do the bias at room temperature, so I'm assuming they want you to set the bias basically right after you turn it on. But what I'm going to do is set them and just let it sit for a while and make sure they're stable. So right now I'm just going through and tweaking them down a little bit. At this point the adjustment is very small. And that's right about where I want to be. I did want to go over a quick note on draining the power supply here. So before I put the fuses back in, I want to make sure that I don't have any voltage on the center points there. So right now I am putting my draining rig across the main filters, which are already pretty far down. And then you also want to go over the output coupling capacitors. So you can see there's a little bit of voltage there. Where are we? Okay, now I'm safe to replace the fuses. And just a note, the fuse for the base, let's see if I can find it here. The fuse for the base on both of the amplifiers here is 1.6 amps on the base and then 1.25 amps on the mid and the treble. Okay, now that the amplifier chassis is completely rebuilt, I wanted to go back and verify that my active crossover values are still set up correctly. So I've set up my 1.9 volts on 15 kilohertz. My stimulus level is slightly different. I'm at 94.1 millivolts RMS, but that could just be right now I'm just manipulating the input control. So it could just be that I was slightly off of 0 when I made that initial adjustment. But the main thing here is I just want to see if this still tracks with that 1.6 and 0.9 volts when I change the frequency. So I'm going to start at the 40 hertz. I'm looking for 1.6. Is that correct? Yes. Okay. And then the other one was 1 kilohertz. And up on my scope, I'm supposed to be getting 0.9. I'm at, sorry, yeah, 0.9. I'm at 0.88. Make sure my mid-range control is zeroed. 0.88. I'm just going to tweak that one out a little bit. Okay, I'm now going to be looking for clipping and max output power. So the mid-range is supposed to be 30 watts, woofer 50 watts, and tweeter 15 watts. So right now I'm at 1 kilohertz. We're going to be testing the mid-range. I'm starting to get pretty severe clipping down here, but not on the top. I'm wondering if my something might not be quite correct there. That's where I'm clean. And that's showing 10 volts RMS into 8 ohms. 10 times 10 is 100 divided by 8. That's only 12.5 watts. That's really low. So I might have an issue there in the mid-range channel. Let's see what the other ones look like. So I'm going to do 15 kilohertz. My stimulus is way too high there. Let's bring this down. Okay, so we have tweeter here. This is only supposed to make 15 watts. I'm already at about 13, 14 watts here. So let me just creep this up. Make this a little bigger. That's starting to clip there. And I'm at right about 15 watts. So the tweeter is doing okay. It looks like it's clipping on the bottom half of the waveform first, and we're going to be looking at the center point here in a little bit. So tweeter does look good, slightly off center, but it's pretty good. And then let's go to the bass, 40 hertz. And I gotta bring up my other channel. Let's see, trigger. Channel 2. Okay, right now that's about 10 watts. I'm going to up my input signal. All right, we're into the next range. That's over 50 watts right there. And we're not even clipping yet, which is great. Clipping's right there. Yeah, so the bass and the treble amplifiers are doing great, but the mid-range is not happy. The amplifier on the left here is the one that we've been working on most recently, and this one has the issue with low output on the mid-range channel. And shame on me for not doing an intermediate test. So on this one, I rebuilt this crossover board. We set the levels and stuff, but at that point, when this was still original, I didn't ramp it up to rated power. So after rebuilding this, I'm having an issue in the mid-range, and I don't know which section it's in. So the first thing that I looked at was the center voltage. So on capacitor coupled designs, the speaker output is floating at half of the power supply rail. So I had about 64 volts here and 32 volts at the center point. So I didn't think it was going to be the amplifier, because that asymmetrical clipping would have required that center point to be way off of center. So the next thing I looked at was just a physical inspection. Maybe I did something wrong on this guy. And the first thing I did was I just compared this channel to this channel, and I found that I have one cap that's backwards. So this guy here is, I think, in reverse, and this lines up with the mid-range control. So I'm going to swap the polarity of this capacitor, and hopefully that fixes it. So I'm going to swap this out, and then we'll redo the test on this chassis. Okay, so C544 is in question. There's a marking on the board with a solid line that indicates negative. So let's see if I did indeed install this one backwards, or if it's the other channel that's messed up. Yep, so this capacitor is supposed to be in this way. I think this is going to fix the problem. So just because this one was operating in reverse polarity, I'm going to put in a brand new cap just in case this one was damaged. Okay, I've got that capacitor flipped around. Unit is powered back on. We are at 1 kilohertz. This is about the level that we were clipping before. Still going strong. And there's clipping at the top there. There I'm clean, 17.7 volts RMS, 17.7 times 17.7. And we're at 8 ohms here. 39.16 watts. That's pretty good. So on there we were supposed to make at least 30. So it was definitely that backwards capacitor, and now both chassis are fully up and running. Okay, so what I have on the page here is a comparison of the performance of both amplifier chassis against the spec from the manual. So I'll just go through what I've done here quick and show what else I need to work on. So let's start out with clipping power. So this is just testing each channel up to its actual clipping power. Now it's rated at 40 watts, 30 watts, and 15. It performed better than expected at 40 hertz and 1 kilohertz, but the tweeter amplifier was under by 1 watt on both amplifiers. But what I'm looking for is consistency, and these are performing almost exactly the same. So that's what I wanted to see. And then this was another one I was concerned about. So before I recapped the crossover board on the second amp, this took about 111 millivolts RMS to drive to the 1.9 volt reference level. Now, after everything's rebuilt, I have 95.2 to drive it to that level, and the other chassis, this is with all the controls at 0, is 95.0. So that's close enough for me. My problem here in this area is I can't get the level of the mid-range amplifier down to the proper level. So it's supposed to be at 900 millivolts RMS, and I can only adjust it out to 936 millivolts. So that's one section that I'm going to be looking at further on the second chassis and see if I can add a resistor or alter a value so that I can get a little bit more adjustment range. For THD, I didn't go crazy. The spec is 0.1%. That's pretty darn easy to reach. And even with my Siglent oscillator, which is at 0.08% THD on average, I'm not really showing any THD on the mid-range amplifier, so I just skipped the rest of the testing on that. These waveforms look clean, and again, that 0.1% is pretty easy to reach. So the THD I wasn't too concerned about. Frequency response. So the way that this works is they're telling me to set a reference frequency. This is with a dB reference, so I can do this with either my Sencor PA81 or my Panasonic, and I actually use them both. I use the Panasonic analyzer for the mid-range because that's tied into my 8 ohm load, and then for the 4 ohm loads I use the PA81 Sencor. Set a dB reference for each one of these levels and then compared it against the spec. And again, it's very close channel to channel. So my -3 dB down point was 165 hertz when I was working on the low frequency amplifier. So I set a reference at 75 hertz, and then I changed the frequency of my signal generator until I reached -3 dB. and that was the frequency at which that happened. In the other channel, it was at 160 hertz, so very, very close here. And then this is the mid-range, has 2 points because it's crossing at the low and the high end of its performance. So at the high end, I had 2470 and 2476 and 438 and 436. So again, very, very close. And then finally, almost exactly the same performance for the roll-off for the tweeter. You can see it doesn't match exactly. This was supposed to be 7 kilohertz. I was at 7.1, 400, 436. So it doesn't match perfectly to spec, but they're super close to one another, which is what we want. And all this means is that my amplifiers have the correct frequency response. So they're cutting the highs and the lows at the proper frequencies for optimal driver performance. So I'm happy with this so far, except for this one value. So that's the one last thing I need to solve before I can call this project complete. Okay, we're looking at a schematic for the active crossover network for the mid-range section only, and the area of interest is right here. So this is where the 2.5K trimmer is for adjusting the overall level. This is what we're adjusting to try to get that 0.9 volts in reference to the 1.9 volts when we're feeding in 15K to the treble amplifier. So what's happening is when I have this control fully adjusted to one direction, it's still not enough adjustment for me to make the proper change. So one of the challenges with this project is this schematic does not match the boards that I have in the unit that I'm working on, and it really doesn't even match itself. So in the service manuals that I have access to, this diagram doesn't really match the board layouts either. This capacitor, 1 microfarad here and here, those are all actually 10 microfarad on my boards. This resistor I was hunting for doesn't actually exist, so when I redrew this, I found that the emitter just comes straight to one side of this adjustment trimmer. So that resistor here doesn't even exist. There is an R554 on the board, but it's not for that. It's actually this one. This is shown here at 2.2K, but in my unit it's 1.8K. So that's this guy here, and it's the same value that's in the other amplifier. So I'm not exactly sure what was going on here, but in any case, this is forming a voltage divider, and I figure by adjusting this value, I can get into the adjustment range that I need. So what I have set up here is I've removed that 1.8K resistor and just soldered in a couple of temporary hookup wires, and those are clipped into a decade box. So right now the decade box is set to 1 in thousands and 8 in the hundreds. So this is 1.8K. So I'm simulating the resistor that was in there, and we're looking at the 1K waveform here. And right now my level is 961 millivolts, and we're looking for 900. So this is with the control all the way maxed out, and what I found is if I adjust this down even just 100 ohms, so now we're at 1.7K, I'm at 930, adjust down again, 899, again 863. So I should be able to alter this resistor value and get exactly the level that we're looking for. So what I'm going to do first before I pick a resistor value is I'm going to adjust the trimmer to the center of its range. Okay, that's now centered, and that's at 1.5 volts. So I'm going to just drop this down. Let's see, hundreds. I'm just going to continue dropping this. So now that's at 1K, still not low enough. So I'm going to put this back up. We'll put this back up to 8, drop this down to 0. So now we're at 800 ohms. Continue to go down. I don't know if this is going to do the trick. I think we're going to have to come up with a combination. I'm going to go with a nice even value 1K and just rotate the trimmer and see if I can get down to 0.9. So this is a little bit of trial and error here, but I think I can get this where it needs to be. Yeah, so I'm already, with 1K in there, I'm already able to go way below 900 millivolts. So let's bring it up somewhere around there. And my control's at like, I don't know, maybe 20%. So that's good. There's still adjustment range above and below. So I'm going to go ahead and substitute out this 1.8K with a 1K and redo the test. Okay, now that that resistor's in place, let's see if we can get this thing calibrated properly. So I'm going to turn it on. There's our 1 kilohertz. That's pretty high. Let me make sure I have range here. So this is showing me 995. Yeah, I've got the proper range there now. Okay, so let me take it back to 15 kilohertz for the frequency, 1.9, 40 hertz, 1.6, and 1 kilohertz. I'm at 910 millivolts, so I can just slightly adjust this. Jumping between 899, 898, I think that's going to be close enough. So now both of my channels match on all parameters, and I think that's going to do it. While I had the rat's nest of cabling connected here at the bench, I thought it would be a good opportunity to do a 3-channel Bode plot. So what we're seeing here on the scope is a plot of the 3 amplifier channels. Green is bass, blue is mid, and yellow is treble. So you can kind of see the relationship in amplitude as the frequency changes. So we have 20 hertz down here and 30 kilohertz up here. Here is the Bode plot of the second amplifier, and I was very pleased to see, if you look at the blue trace, the mid-range, as it comes up to 1 kilohertz, it lands right on the 0 dB mark. That's the reference that I set when I tested the first amplifier. So these amps have very similar amplitude, and the shape of the green and the yellow traces are very similar at the extremes of frequency. So these amps have very similar performance, and that's exactly what we want in a 2-channel system. Okay, that's going to wrap it up for this video. I will be doing a part 2. In the second part, I will build a custom interface box that will convert RCA to DIN so that we can connect these speakers to a conventional source or preamp. I'll also be incorporating a remote power on-off circuit that takes advantage of the built-in relay infrastructure in the speakers so that we can power on and off via an external toggle switch or from a switched outlet on a preamp, something like that. And then if we have time, we'll load the amp chassis back into the speakers, reassemble everything, and see how it all turns out. So if that sounds cool, definitely look out for part 2. Thanks again for coming by the channel. If you like this content, I would encourage you to subscribe, and we'll catch you on the next one.